All right. So my name is Dale Bustad. I will be talking today about HTTP2 server push, one of the features that was included with the new protocol. And so that I can avoid stumbling over my words as I go along, I will be referring to HTTP as H. So H 1.1 or H2. I think it will probably go massively better that way. I work for Formidable in Seattle, Washington. I'm a software engineer. We are a software consultancy at the moment specializing in node.js and React. So if you have a project coming up, please feel free to reach out to us if you think we can help. I'm not very good at talking about myself, and as I was trying to think of what to share, I realized that maybe I could just check my LinkedIn profile. So here's a list of things that apparently LinkedIn thinks I am qualified in. And I don't know if you noticed at the bottom. So if you see me exhibit either of these qualities during the talk, I will take as many endorsements as I can get. Yeah, so I have a lot to get through, so I'm going to jump right in. Rewind a few years to H1.1. This was adopted in 1999, but was in practical use for a couple of years before then. And I want to give you a quick feel for the contemporary technologies of the day. First up, we have the BlackBerry 850. This was the first BlackBerry to hit the market. Super Smash Bros. Was released for the N64. This was significant in my life. And the first iMac had just been released. Apple has come quite a long way since then. And you might point out that a lot of modern technology is built on older ones. And you would be right, but the web has come quite a long way since then. So here's a look at GeoCities of 1999, thanks to archive.org, also yahoo.com, and AOL.com. Now, if you look closely, you'll see that this was almost universally static content, which meant very simple transactions between the client and the server. And then more pertinent to you and me is how JavaScript was used back then. So here are some of the features that had just landed in 1999. First up is regular expressions. That had just been introduced in 1999. The undefined global was introduced. Strict equality had just been introduced. Previously, double equals was all you could use. Throwing and catching errors was introduced. This is rather illuminating. This is the foundations of the JavaScript language. But notably, there was no Ajax until 6 years later. And this was the world that H1.1 was built for. So fast forward to present day in H2. It was officially adopted last year. And here are the first 45 pages of the spec. I was going to try to include all 100, but I couldn't fit it on the slide. I'm not going to take you through the spec because I think you'd probably kill me. But that doesn't mean that getting a feel for how this stuff works wouldn't be useful for us in our day-to-day work. So in that light, I'm going to take us all through the evolution of the web from its infancy through H2 in the form of a child's narrative. You'll see some labels pop up to hopefully tie these concepts together with the real things. So with that, I give you the Browse Chronicle. Long ago, in the vast land of network topology, lived a good queen in an old castle in the city of Browse. Queen Client was a good queen, and although her people were happy and well taken care of, they were isolated and knew little of the outside world. The queen aspired to more, both for her people and for her kingdom. And so she formed a corps of messengers and couriers whose mission it would be to seek out friends in the neighboring lands, to form treaties and partnerships that would multiply the prosperity of all involved. Among those messengers was a man by the name of Packet. Like other messengers, he was young and inexperienced, but full of exuberance. And so full of purpose, Packet was set out on his trusty steed Lan to explore the surrounding lands and report back to the queen. But as the queen's couriers expanded their reach, they eventually came across unexpected perils, One of these you see here was the magical forest of mirrors. To the queen's horror, one of her messengers would enter the forest, but one or more or none would come out. Not only that, but the messengers would arrive out of order, and the messages themselves would sometimes be damaged, and it was difficult to know whether the messages had ever even been delivered. So, of course, this wouldn't do. And the queen consulted her royal court in hopes that a solution might become evident. And to the queen's delight and everlasting favor, the royal scribe had an idea. Tia Saipia was her name, and she devised a plan. Tia came up with a methodology to uniquely identify each message going out and give them an order. This way, when messages were received, they would know which one was sent first and what to do with it. She also came up with a very simple cipher code that they used to identify whether a message was intact. Now, due to the massive success of this endeavor, Tia Saipia secured for herself some very serious job security, as well as a sizable stipend and a room in the palace. And all was well for a time. The kingdom thrived and its people prospered. Packet and his friends were able to extend the scope of their travels. They traveled along the river router that you see here, and all across the great land of network topology. As you might expect, through their explorations, they discovered other friendly kingdoms. And so in order to cultivate these burgeoning friendships, they made arrangements with these foreign kingdoms and came up with a system to pass along messages from one kingdom to the next. This was very good for Packet, as he finally had a destination in his travels, and it didn't hurt when he made friends with Nat, a beautiful courier from neighboring land. And as her network of messengers grew, Queen Client and her partners established a worldwide web of information and connectedness. But not everyone they met was friendly. As they expanded further and further into unknown lands, Packet and his friends began to encounter ruffians, bandits, and rogues. These rogues were quite unfriendly, and most of them carried axes and hatchets. They called themselves the hackers. They would sometimes intercept the couriers just to rifle through what they carried. Some couriers were assaulted and never seen again. And the worst of these bandits would blackmail the couriers, threatening their family, replacing their parcels, and forcing them to betray their queen by delivering a false message. Now, although it was never confirmed, it was rumored that certain neighboring monarchs employed these ruffians in an attempt to gather intelligence about their neighbor. Of course, this was not a situation the queen could abide. They tried many things. They sent extra messengers, but that rarely helped. They attempted to secure the roads that the messengers would take, but this was politically untenable and very costly. And so the queen sent out her best knights to search across the known lands, seeking someone or something that could help them mount a defense. Eventually, they found a Cecil, the encryption mage. Now, a Cecil was old and somewhat unsociable, but he also possessed the exact skills that were needed. And so, after much negotiation, he was brought back to the castle and entered the queen's employ. From that point on, whenever a message was to go out, it would first be brought to him. For each of these messages, he would put a spell on it, such that only the recipient could read it. And in fact, his magic was so strong that the spell would extend to any messages sent in response. Now, this turned out to be very effective. With no one able to read the messages, the attacks slowed considerably, and with the queen's increased reach, she began to build outposts far from the city of Breze. But there was a downside. As I mentioned, Cecil was old and pretty grumpy, and he didn't like being bothered all the time. Very few people react well to being woken up in the middle of the night with urgent work to do, and Cecil the encryption mage took it worse than most. So it took considerable time for Cecil to do his work. Sometimes the queen would receive a message and want to send an immediate reply, but she couldn't. And her ability to respond to dire situations suffered. And so the queen charged her advisors once again to come up with a new scheme. Sir Ver was the bravest and noblest of the queen's servants, and unwavering in his loyalty to the queen. And as leader of her largest outpost, he was intimately aware of the problem at hand. Sir Ver gathered together Packet and his cohort, TSIP of the scribe, Cecil the encryption mage, and many other wizened advisors of the queen and of their allies. And after much deliberation and discussion, a new scheme was devised with new techniques, whereby the responsiveness of Her Majesty's forces would improve by significant margin. Of note, a Cecil would only have to cast an enchantment for each new recipient, instead of for every message, much to his relief. And the Queen's servants also identified strategies to send extra information with the messengers, cutting out much of the back and forth communication. These changes brought about a great new age for the city of Browse, and eventually, all was well. The kingdom thrived and its people prospered. All right, so there you have the history of the web. And let's just take a quick step back. Thank you. Queen Client obviously is the HTTP client, your browser, and a browser requests resources of the server, right? In our story, the Queen was asking for intelligence reports, but it could have just as easily been cat videos. At the end of the story, the Queen encountered a number of problems. We encountered them too with H1.1. There's too much back and forth. There's the need to repeatedly renegotiate an SSL connection. There's lots of overhead and latency with each request. So let's frame this up in a more practical way for you and me. In 2010, Mike Belsch wrote a paper detailing the relationship between bandwidth, latency, and page load times. And we all want fast page load times, right? That translates into dollars. So here's what he found. As bandwidth increased, page load time improved, but the relationship is basically logarithmic. After 5 megabits per second or so, page load time essentially did not improve no matter how much extra bandwidth you throw at it. The extra bandwidth was ultimately just not very useful. Now, in comparison, if you look at page load time as a function of the round trip between the client and the server, this is what you see. It's basically a linear relationship where every 40 milliseconds or so you cut off the round trip, load time improves by about half a second. These numbers were generated by capping bandwidth at 5 megabits per second. Now, the conclusion we can draw is that latency has a much larger impact on page load time than bandwidth in a high bandwidth environment, much like we're often working with in the United States. It is worth noting that Mike Belsch was an early engineer on Google's Chrome browser, as well as co-creator of Speedy, which eventually became H2. So you might see where I'm going with this. Many of you will have seen something like this while developing a web application. You open up your dev tools when you watch a page load, and you'll see a cascading waterfall of requests. With H1, you'd have these repeated SSL negotiations for each request, right? And in our example here, the browser would only request the dependency once the JavaScript entry point that required it was loaded in the browser. And there's a couple caveats here. H1.1 does this for a couple of reasons. Normally, connections with a particular origin are capped at 4 connections at a time. So of those 4 connections, that's loading JavaScript, that's loading images, that's loading all your content. And so typically, you'll see these cascading effects because many of those connections are going to be consumed loading images and other things. But if you think back to the web pages I showed you from 1999, this makes perfect sense. They were mostly static, and they didn't need to worry about the back and forth between the server and the deeply nested dependency graphs. Moving on, here's what the same page would look like if you were to use H2. You'd have a shared SSL context. You have highly concurrent downloads from the same origin. And ideally, server push would intelligently send files to the browser that we know it will need, sidestepping bandwidth or latency issues altogether. That is, if our server is smart enough. Now, it might occur to you that the server could send files to the browser that it already has cached. Well, an H2 connection is composed of a set of streams, each representing a different resource. And each stream is composed of a number of frames. With a normal request, the stream would have a header frame, followed by a number of data frames. However, in the case of server push, the server first sends a push promise frame. And when the browser receives this, it can respond with a reset stream frame, which will cancel the stream and stop the server from sending any additional data. In most cases, there will already be data in the pipe. But as we established earlier, using up a bit of extra bandwidth is a pretty fair trade for reduced latency. Okay, so next question. Can I use it today? Can I actually use this thing? Let's start with browser support. All major browsers support H2 today. Some of these have supported it for a while, some of them are rather new. This translates into approximately 75% of users worldwide browsing with H2 support. That's from Can I Use. In the US, it's close to 90%. That's for both mobile and desktop. Now, server support has taken a bit of time to catch up, but it's starting to look pretty good. We have Apache and Nginx both supporting H2, although Nginx does not yet include server push support. Both Akamai and Cloudflare include H2 with server push support. They have different APIs for defining what to push, but they're both there. And other CDNs plan to be following suit very soon. Okay, so now kind of to the crux of all this. This is a JavaScript conference. What about bundling? And this is where I want to focus when it comes to server push. How does it affect how we build and deploy single-page applications? There are some significant implications here. The foundations for most of our present-day code deployment strategies is file concatenation. You take a bunch of things, you kind of stick it together, it goes down the pipe. H2 could make a number of these strategies obsolete, including some of the recent additions. Tree shaking, for example, which is just a specialized form of dead code elimination, may not look as beneficial if we can split up our application into small modules, serve up individual files without any performance hit. And bundling in general starts to look much less attractive, potentially harmful to our application's performance, in fact, since most bundles will include code that your client doesn't need. So now you might be thinking, what should we do instead? Oh, skipped a slide, sorry. H2 sounds completely incompatible with entire ecosystems of tools that we rely on, with our entire workflow. This has been something of an open question in the JavaScript ecosystem, and I do expect a number of solutions will be presented over the next couple of years. But I'd like to introduce you to a potential solution, which you already got a sneak peek of, in a project that I've been working on the side for a little while now. Oh, now it's playing. There we go. All right. Interlock.js. I could do an entire talk on the internals and design decisions that went into this project, but for today I'm going to try to keep it pretty simple. Interlock is a bundler and build pipeline. It takes a lot of input files, it transforms them in some way, it combines them in some way, and it outputs the result, right? And it incorporates a runtime component akin to Require.js or Webpack's runtime. A couple of highlights. Let's see if this animation works. It does, good. This is a piece of interactive documentation I've been working on. It allows you to explore the compilation process and understand the steps that are taken and how to override them. There's been a lot of time devoted to making Interlock comprehensible for people who want to know how it works internally. And in fact, a lot of that internal API is exposed and is the way you affect compilation. Interlock is also reaching a critical mass in its feature set. We have JavaScript support through Babel, and it uses AST as the intermediate format from end to end during compilation. We also have support, first-class support for CSS, which means there's no need for things like the extract text plugin if you've run into that in Webpack land. It has first-class support for HTML, which means you can write JavaScript or CSS inline in your HTML file, and it will be transpiled along with the rest of your code. It supports code sharing across builds, so you can split a big monolithic build into lots of smaller builds that interoperate and are reusable. It supports transpiling your node code too. So in Webpack land, there is a node target, but it's kind of clunky. It comes out as a single file, and the require semantics have completely changed. With Interlock and its node support, you get the same sort of behavior as you would get in the browser, which means if you're using CSS modules, you're just getting a lot of class names back. All the templating works the same. It just works the same as it would in the browser. Thanks to my coworker Tyler, who's in the audience somewhere, we have support for Webpack Loaders, as well as browserify transforms. And then there are some other integrations like handlebars and Uglify and runtime interop with the required JS runtime. We are approaching feature parity with Webpack, both through the plugins or direct customizability. And it's extremely extensible. Everything on this list, except for the very first, is provided through a plugin. But finally, it supports an H2 optimized output, including a server push manifest. This is a plugin. It is optional. And I want to answer the question, like, what does H2 support actually look like? What does server push support look like? To answer those questions, let's look real quick at how bundling works. Let's say you're using Webpack, and you're starting with a single entry point A. That requires in a few other JavaScript modules. And as it discovers these files, Webpack will assign each of these modules a number, which ends up becoming its module ID. At the end, by default, you end up with one bundle. That works fine as a simple case, and it's great in the H1.1 world. And you can also define other entry points and split points. You can end up with two bundles, one for each entry point. But what it can't really do is to generate the same number of output bundles or files as you have input modules. And also the lack of robust asynchronous support for interop between multiple builds and the constraints of its module system means that Webpack bundles from different builds don't play nice with each other on the same page. In contrast, Interlock's modules are assigned an ID that represent unique behavior, both of the module and of its dependencies. The conceptual data structure is called a Merkle tree. Its inspiration came from Git's object storage graph, if you're interested in that. In practice, this means that builds don't conflict. They work together well and cooperate. Modules can be arranged into bundles in any way that's desired without any additional complexity in the runtime or build system. And also, the module hashes can be mapped directly to file names. So just wrapping up here to take, for example, a very small application consisting of a single entry point. It'll also have a child module, and it'll pull in Lodash just for a third-party dependency. The output would include, and I'm sorry this is going to be very small on the screen, a single entry point bundle and its source map, a ton of individual files, all mapping to an input file, with file names guaranteed to represent unique behavior, which helps immensely with caching. And finally, a push manifest file that your server can use to know what else to push when a file is requested. There's not a lot of standardization yet for this sort of manifest. Everybody kind of uses something different, but it should be easily transformable to whatever H2 hosting solution you end up using. I am about out of time, so I want to thank you all for listening. But before I finish, just a couple of quick things. If you want to learn more about Interlock, the link is on the screen. I would consider it alpha software, but like I said, we're nearing feature completeness, and it's ready to have folks poke at it a bit. I'm also a co-organizer of Seattle JS. We're a meetup of JavaScript engineers in the greater Seattle area. If you or your company are hiring and you want to get in front of a couple hundred developers to make your pitch, please reach out to me. We are always looking for sponsors and hosts. I also really want to thank Sarah Slater. She's not here today, but she was the artist that did all the drawings for my story earlier. She's a third-year DigiPen student and an illustrator and 3D animator, so you can check out Sarah Slater at the link there. If you want to continue the conversation, I'll be around tonight. You can find me on GitHub or GitLab as divmain, and my email is on the slide. Thank you again. That's it.
Give it up.